In this video, we'll be discussing multivariable optimization. That is, we'll find points of maxima, we'll find points of minima, and we'll also find saddle points in functions with several variables. Now this is a 3D plot of one such function. Now as you can see, this function has point of local maxima, it also has point of local minima, and it also has something called as saddle points, which we'll discuss in short time. Now let us take a paraboloid which is z equals x square plus y square. Now as you can see, it looks like a parabola in 2 dimensions and it has a point of local minima. So this graph, it has a point of local minima at 0. Now we can consider another graph which is z equals minus x square plus y square. It's again a paraboloid opening downwards. So here we have a point of local maxima. Now for saddle points, let us consider this function z equals x square minus y square. Now this is x-axis. With respect to x, this point, it is a point of local minima, and with respect to y, it's a point of local maxima. So this point actually is a saddle point. Now we look at our working method to find points of maxima, minima, and saddle points for multivariable function. So suppose we have a function which is z and is given as f xy. Now first step is we'll find its critical points. For critical points, what we'll do is we'll find zx, which is partial derivative of this function with respect to x, del f by del x, and we also call it as fx, and we'll put it equals to 0, and we'll find partial derivative of this function with respect to y, so del f upon del y, which we also call as fy, and we'll put it equals to 0. Now from these two conditions, we'll get our critical points. And as in the case with functions in two variables, all the points where this function is not differentiable also, we'll include them in critical points. But in this analysis, we are keeping such points out. So now we have our critical point, say a comma b. Now at this point, we need to identify whether it's a point of maxima, or it is a point of minima, or it is a saddle point. So for that, we'll use second derivative test. And for second derivative test, we'll find zxx, that is second derivative of f with respect to x at this point ab, and we'll call it, say, capital A. We'll find b, which is second derivative of the function with respect to y, which we'll also say fyy, and there'll be del square f upon del y square at this point ab, and we'll find c, which is cross derivative of this function. So we'll write it as del square f del x del y at ab, and since we are talking about the points where this function is differentiable, it'll be equal to del square f del y del x at this point ab. So we'll find the value of a, we'll find the value of b, and we'll find the value of c at this point ab. Now we'll find something called as h, and this h is defined as ab minus c square. So this h actually is fxx into fyy minus fxy whole square. So we'll find this value. Now the result is, if h is negative, so if ab minus c square, if this value is negative, then this point ab, it is a saddle point. Now if h is greater than 0, then we look at sign of a, which is fxx, and if it is positive, then this point AB, it is a point of local minima, and if h is greater than 0 and a, it is less than 0, then a comma b is a point of local maxima, and if h is equal to 0, we'll say test fails. So these are the conditions with which we can determine whether at any point there is a maxima or a minima or a saddle point. In the next video, we'll discuss the logic behind condition in second derivative test. Now let us take up an example. Say for example, a utility function is given by the equation u equals x minus 2x square plus xy plus 40y minus y square, where x is number of units of good x and y is number of units of good y consumed. We need to determine values of x and y which maximize u. We have to confirm that the point is a maximum, and also we need to find its maximum utility. So we are given this utility function which is u, x minus 2x square plus xy plus 40y minus y square. Now first step, we'll find its critical points. So we'll partially differentiate this function with respect to x and we'll put it equals to 0. So we'll get 1 minus 4x plus y equals to 0. So we have our first linear equation, and there'll be 4x minus y equals 1. And we'll also partially differentiate this function with respect to y. We'll get this function as x plus 40 minus 2y equals 0. So here we'll get minus x plus 2y equals 40. Now we'll multiply it with 2 and we'll add the two functions. So we'll get 7x equals 42. So the value of x is 6, and if we'll put x as 6, we'll get y as 23. So the only critical point for this function is 6, 23. Now we'll need to confirm that it's a point of maximum. So for that, what we'll do is we'll find a, and which is del square u upon del x square. Now we'll partially differentiate this function again with respect to x. We'll get this as minus 4. We'll find b, del square u upon del y square. So we'll partially differentiate with respect to y. We'll get this as minus 2, and we'll find its cross derivative c. So we have to differentiate this function now with respect to y. So value of c is simply 1. From here also we'll get the value of c as 1. Now we'll calculate the value of h. Now h simply is ab minus c square. Now ab in this case is 8. 8 minus 1, it is 7. So we have this condition where value of h is greater than 0 and value of a is less than 0. Now here there is one more thing that I would like to add. If you want, you can check the condition with b also. It doesn't make a difference because they have same sign. Now when h is greater than 0 and a is less than 0, it simply means this point 6, 23, it is a point of local maxima. Now we need to find its maximum utility. It simply means we have to find maximum value of u, which we'll get when the value of x is 6 and the value of y is 23. So this maximum utility, it will be 6 minus 2 into 36 plus 6 into 23, 40 into 23 minus 23 square. And this value is 463. So our critical point is 6, 23, which is the point of local maxima, and the maximum value of this utility is 463. So this is how we find maxima and minima for functions in several variables. Now let us take another example, and which is we are given a function f, x square y minus 2xy square plus 3xy plus 4, and we need to find points of local maxima, local minima, and saddle points. So first we'll find critical points, and for that we'll find its partial derivatives. So del f upon del x, which we also write as fx, and it'll be 2xy minus 2y square plus 3y equals 0. So we'll take y common and we'll get 2x minus 2y plus 3 equals 0. So from this first condition, we'll get either y equals 0 or x minus y equals minus 3 by 2. Now we'll differentiate partially with respect to y. We'll find fy and it'll be x square minus 4xy plus 3x equals 0. We'll take x common. So it'll be x minus 4y plus 3 equals 0. So we'll get the condition either x is 0 or x minus 4y is equal to minus 3. So now we have 4 conditions. Either y is 0 or x minus y is minus 3 by 2 and x is 0 or x minus 4y is equal to minus 3. So we'll get 4 points. So the first point will be when y is 0 and x is 0. So one of the point is 0, 0. Second critical point is when y is 0 and if we'll put y as 0, we'll get x as minus 3. So the other point will be minus 3 comma 0. Third point is when x is 0, if we'll put x as 0, we'll get y as 3 by 2. And fourth point we'll get from the intersection of these two lines. So we'll subtract second line from first. We'll get minus y plus 4y and it'll be minus 3 by 2 plus 3. So we'll get 3y equals 3 by 2. Value of y is 1 by 2. And if the value of y is 1 by 2, value of x is minus 1. So the fourth point will be minus 1 comma 1 by 2. So we have 4 critical points where we'll need to examine whether they are points of minima, maxima or saddle points. And for that, we'll need to use second derivative test. So we'll find A and that is fxx. So we'll partially differentiate it again with respect to x. We'll get 2y. We'll find B, which is f yy and it'll be minus 4x, and we'll find its cross derivative C, which is either fxy or fyx. So we'll find fxy, it'll be 2x minus 4y plus 3. Now we'll begin with this first point 0, 0. For this first point, A is 0, B is 0 and C is 3. If we'll find H, which is AB minus C square, it is minus 9, and since H is less than 0, 0, 0 is a saddle point. Now we'll take minus 3, 0. So at minus 3, 0, value of A is 0, value of B is 12, value of C, it will be minus 6 plus 3 and there'll be minus 3. Now H again is AB minus C square, which again is minus 9 less than 0. So minus 3, 0 is again a saddle point. Now this third point, which is 0, 3 by 2. Value of A is 3. Value of B is 0. And value of C is plus 1. H here is 0 minus 1. So it is minus 1, again less than 0. So 0, 3 by 2 is again a saddle point. And finally, we have this fourth point, which is minus 1, 1 by 2. So for this fourth point, value of x is minus 1 and value of y is 1 by 2. Now A in this case is 1. Value of B is 4. And value of C is minus 2 plus 3, and which is minus 1. If we'll find H in this case, it will be 4 minus 1 plus 3 and H is greater than 0. So for this fourth point, H is greater than 0 and A is greater than 0, and if H is greater than 0 and A is greater than 0, it's a point of local minima. So we have a local minima at -1, 1 by 2. So out of these 4 critical points, first 3 points, they are saddle points, and this 4th point is actually a point of local minima. Now let us take another question, which is find 3 positive numbers whose sum is 100 and whose product is maximum. So we have 3 positive numbers, say x, y and z. So x, y and z, they are greater than 0 and their sum is 100. So x plus y plus z, it is 100, and we need to find the condition that their product, which is x into y into z, it is maximum. So we can write z as 100 minus x plus y. So we can write this p as xy into 100 minus x plus y. So this p will be 100 xy minus x square y minus x y square. Now we need to find maxima for this function. So again we'll find its critical points. So we'll find del p upon del x, and it'll be 100y minus 2xy minus y square equals 0. So we'll get either y as 0 or we'll get 2x plus y as 100. Now since x, y, z, they're positive, so we won't consider y equals 0. Now we'll differentiate p with respect to y. So we'll get 100x minus x square minus 2xy equals 0. And from here we'll get either x equals 0 or x plus 2y equals 100. Again we'll discard x equals 0. Now we'll solve these two conditions. We'll get x equals 100 by 3 and y equals 100 by 3. So our critical point is 100 by 3 and 100 by 3, and we'll need to find out whether at this point there will be a point of maxima. So we'll find A, which is pxx. So we'll differentiate again with respect to x. We'll get minus 2y, which in this case is minus 200 upon 3. We'll find b, which is pyy, and here will be minus 2x, which again is minus 200 by 3, and we'll find cross derivative pxy. So we'll differentiate this with respect to x. We'll get 100 minus 2x minus 2y. Now it will be 100 minus 2. Now x plus y will be 200 by 3. So we'll get this as minus 100 by 3. Now we'll find the value of h. Value of h will be AB, and there will be 40000 upon 9 minus 10000 upon 9, which is greater than 0. So we have this condition where h is greater than 0 and a is less than 0, which simply means this point, it is a point of local maxima. So product of these three numbers will be maximum when the value of x is 100 by 3, when the value of y is 100 by 3, and the value of z is also 100 by 3. And that is the answer to this question. Now in this video, we'll explore the rationale behind second derivative test. Now in order to understand the rationale behind second derivative test for multiple variables, we'll try and understand the logic behind second derivative test for functions in two variables. Suppose we have a function y equals fx and f dash x is 0 at say x equal to a. So x equal to a is a critical point in this case. Now from Taylor's series, we know that we can write fx as fa plus f dash a into x minus a, f double dash a into x minus a square upon factorial 2 plus f triple dash a x minus a cube upon factorial 3, and this series will continue. Now we can write this as fx minus fa. Now a is a critical point, and if a is a critical point, then at a f dash x is 0. So this term will be simply 0. So we'll get f double dash a into x minus a square upon factorial 2. Now when we say point of local maxima or local minima, it simply means that we are looking at the value in the neighborhood of a. So that means this x, it is a plus or minus h, where h is nearly 0. So it simply means that this x minus a, it's a very small quantity, and if it is a very small quantity, then as the power increases, the value decreases. So we can ignore higher powers of x minus a. So we get this result, which is fx minus fa, it is equal to f double dash a upon factorial 2 x minus a square. Now if f double dash a is greater than 0, in that case we can write fx minus fa is greater than 0, which simply means that fa is less than fx for all the points x in the neighborhood of this point a. So it simply means that this x equal to a is a point of local minima. So if second derivative is positive, it simply means that this point is a point of local minima. And if second derivative is negative, then we'll get f double dash a less than 0, which means fx minus fa is less than 0. That is, fx is less than fa. So for all the points in the neighborhood of a, the value of this function is less than the value at this point a. So it means that this x equal to a, it is a point of local maxima. And if f double dash a is 0, then in that case we'll have to look for sign of f triple dash a. So that means now this second derivative test is inconclusive. Now we'll try and figure out the rationale behind second derivative test for multivariable functions. So suppose we have a function, say z equals fxy, and we have a critical point at ab. Now again we'll use Taylor's expansion for two variables. So we can write fxy equals fab plus fxab into x minus a plus fyab into y minus b plus 1 by 2 fxx x minus a square plus 1 by 2 fyy y minus b square plus fxy x minus a y minus b, and this series will continue. Now we know that at critical point a and b, first derivative fx, it is 0, and fy is 0. So both these partial derivatives, they are 0. So we can write this as fxy minus fab, and it'll be equal to 1 by 2. Now we have taken fxx as a, so it'll be a into x minus a square plus 1 by 2 fyy is b, so it'll be b y minus b square and plus c x minus a into y minus b plus all other terms. Now again we are looking for points of local maxima and local minima. That is, we are looking for the points in the neighborhood of a, b. We can ignore higher powers of x minus a and y minus b. So we can write fx minus y minus fab, it is nearly 1 by 2, and then a x minus a square b y minus b square plus 2c x minus a into y minus b. Now here what we'll also do is we'll take y minus b square common from this bracket. So we'll write 1 by 2 y minus b square. So we'll get a x minus a upon y minus b square plus 2c x minus a upon y minus b and plus b, which is a quadratic equation in x minus a upon y minus b. So we'll take x minus a upon y minus b as some variable, say t. We can simply write f xy minus f ab as 1 by 2 y minus b square at square plus 2ct and plus b. Now this expression, it is already positive, so everything will depend on sign of this quadratic expression. Now we know that if a is greater than 0 and if d is less than 0, then this quadratic expression at square plus 2ct plus b, it is always positive for all t belongs to R. So it simply means that in that case fxy minus fab, it will be greater than 0 in the entire neighborhood of ab. So we'll get this condition fxy is greater than fab. So for all the points in the neighborhood of ab, the value at ab is the lowest. So from here we can say this fab, it is a point of local minima. Now what is the condition? We need to find d. Now d for this function is 4c square minus 4ab. So condition here will be a is greater than 0 and d, which is 4c square minus 4ab, it is less than 0. So from here we'll get ab minus c square, which is our h, and h is greater than 0. So this function, it will have a point of local minima when h is greater than 0 and when a is greater than 0. Now if a is less than 0 and d is less than 0, then this quadratic expression at square plus 2ct plus b, it is less than 0 for all t belongs to R. So it simply means that fxy minus fab will always be less than 0. So we can write fxy is less than fab, which simply means that this fab, it is a point of local maxima. So we'll have a point of local maxima when a is less than 0 and d is less than 0. And d again is c square minus ab is less than 0, which means h, which is ab minus c square, is greater than 0. So if we have h greater than 0 and a less than 0, then it will be a point of local maxima. Now if d is greater than 0, then this quadratic expression, whether opening upwards or downwards, somewhere it will have positive value and somewhere it will have negative value. So in that case, this point, it will have a value which is greater than value at some points, and it will have a value which is less than value at some other points. Then in that case, it will simply be a saddle point. And if d is equal to 0, then again test fails. So that is the logic behind second derivative test for multivariable functions. Now in this video, we'll discuss how to find maxima and minima if we have more than two variables. So if we have any function having n variables, x1, x2 and xn equals to 0, and we have to find its maxima and minima, first step again will be to find partial derivatives. So we'll find del f by del x1, we'll put it equals to 0. Del f by del x2, again we'll put it equals to 0. And del f by del xn equals to 0. And we'll find critical points. Now for second derivative test, we'll find f11, which is del square f upon del x1 square f12 del square f upon del x1 del x2 f13 del square f upon del x1 del x3, and in the same way we can find f21 f22 f23 f31 f32 and f33, and we'll define this Hessian matrix as f11 f12 f13 f21 f22 f23 and f31 f32 and f33, and then we'll find determinant for this matrix. Now looking at the sign of f11 and delta h, we can say whether the given point is a point of local maxima or a point of local minima, or it is a saddle point. If h is less than 0, we know that it's a saddle point. If h is greater than 0 and f11 it is greater than 0, it's a point of local minima. If h is greater than 0 and f11 is less than 0, it's a point of local maxima. And if h is 0, we simply say test fails. Now let us take up an example. Say for example, we are given this function x cube plus y cube plus z cube minus 9xy minus 9xz plus 27x, and we need to find whether this point 3, 3, 3 is a point of local maxima or a point of local minima. So first we'll find its critical points. So we'll find del f by del x. So it'll be 3x square minus 9y minus 9z plus 27 equals 0. So from here we can write x square minus 3y minus 3z plus 9 equals 0. We'll find del f upon del y, and there'll be 3y square minus 9x equals 0. That is, value of y square is simply 3x, and we'll find del f upon del z, and it'll be 3z square minus 9x equals 0. So we'll get z square equals 3x. Now from these two conditions, we'll get y square equals z square. That is, either y equals z or y equals minus z. Now we'll take y equals minus z and we'll put y as minus z in the first condition. We'll get x square plus 9 equals 0, for which we are not getting any real roots. So we discard this condition, y equals minus z. So the condition that we'll consider here is y equals z. Now we'll put y equals z. We can write this first equation as x square minus 6y plus 9 equals 0. And this x is y square upon 3. So we'll put x as y square upon 3. We can write y to the power 4 upon 9 minus 6y plus 9 equals 0. So it'll be y to the power 4 54y plus 81 equals 0. Now one of the root of this equation is y equals 3. If we'll put y equals 3, it will satisfy this equation. Actually, this equation has another root which is very weird. So we won't discuss that root in this analysis. Now since y and z are equal, so if y is 3, value of z is 3. So we'll get y equals 3 and z equals 3. Now we'll put y as 3, we'll also get x equals 3. So our critical point, it will be 3, 3, 3. So that's our critical point. Now once we have our critical point, we'll find fxx. Now fxx, it'll be simply 6x, and in this case it'll be 18. Fxy, so we'll differentiate this with respect to x, we'll get minus 9, and then fxz. Fxz will be simply minus 9 again. Now fyx, so we'll differentiate this with respect to y. We'll get this as minus 9. Fyy again will be 6y, which is again 18. Fyz, fyz is 0. Fzx, fzx is minus 9. Fzy will be simply 0. And then fzz will be 6z, and again which is 18. Now we'll find this Hessian determinant, and it will be 18 minus 9 minus 9 minus 9 18 0 minus 9 0 and 18. Now we'll solve this determinant. Its value, it comes out to be positive. So here we have this condition where h is greater than 0 and fxx is also greater than 0, which simply means that this point 3, 3, 3, it is a point of local minima. So we'll have a local minimum value at this point 3, 3 and 3. Now there will be some questions on absolute maxima and absolute minima for multivariable functions. Now what do we do in such cases? So in such cases, first step again is we'll determine all the critical points, and here we need not use any derivative test. We just need to find critical points. Second, we'll find the maximum and minimum value of this function over the given boundary curve. And third, once we have all these points, we'll put the value of these points in the function, and we'll select the largest and smallest value of this function, and whichever value is the highest, that's your absolute maximum value, and whichever value is lowest will be absolute minimum. Say for example, we are given this function fxy, and it is x square plus xy plus y square, and we need to find its absolute maxima and minima over the circular region x square plus y square less than or equal to 1. Now first step, we'll find its critical points. So del f upon del x will be 2x plus y equals 0, and then we'll find del f upon del y, and here it will be x plus 2y equals 0. From solving these two, we'll get one critical point, and there'll be 0, 0. We'll also find value at 0, 0. Now value of this function at 0, 0 is simply 0. So value of f00 is 0. Now second step is we need to determine the maximum and minimum value achieved by this function over the boundary curve of R. Now in this case, the region is this circular region x square plus y square less than equal to 1, and the boundary curve for this region will be x square plus y square equals 1. Now we need to find maximum and minimum value of this function on this boundary curve. Now we know that any point on circle, we can take this point as a cos theta and a sin theta, where a is the radius of the circle. Radius is 1. So we can take this point as cos theta comma sin theta. So we can write f cos theta comma sin theta as x square, which will be cos square theta plus cos theta sin theta plus sin square theta. Now sin square theta plus cos square theta will be 1, and then if we multiply and divide it with 2, we can write this as 1 by 2 sin 2 theta. Now minimum value of sin 2 theta is minus 1. So in this case, minimum value of this function, it will be 1 minus 1 by 2, and that is 1 by 2. And for maximum value of this function f, we know that maximum value of sin 2 theta is 1. So here this value is 3 by 2. Now we have three values, 0, 1 by 2 and 3 by 2. Now out of these three values, 0 is the lowest value. So absolute minimum value of this function, it is 0, and highest value is 3 by 2. So absolute maximum value of this function is 3 by 2. And if you want, we can also write points of maxima and minima. So we'll get minima at 0, 0, and we'll get absolute maximum where the value of sine 2 theta is 1. So we'll put sine 2 theta is 1. We'll get 2 theta as either pi by 2 or 5 pi by 2. That is, value of theta will be either pi by 4 or 5 pi by 4. So if we'll put theta as pi by 4, one of the point will be 1 by root 2 comma 1 by root 2, and the other point will be minus 1 by root 2 and minus 1 by root 2. Now let us take another example, which is find the absolute maximum and minimum of this function xy minus 3x on the region x square is less than equal to y is less than equal to 9. So first we'll find its critical points. Del f upon del x will be y minus 3 equals 0. So we'll get y equals 3, and then del f upon del y, which is x, it is 0. So we'll get x as 0. So one of the critical point will be 0, 3. And then we'll find value of this function at 0, 3. This value will be simply 0. Now second step is we'll need to find minimum and maximum value of this function at the boundary curve. Now here we have two boundary curves, y equals to 9 and y equals x square. Now we'll take y as 9. We can write f x comma 9 and it'll be 9x minus 3x, which will be simply 6x, where the value of x will lie between minus 3 and plus 3. Now this is nothing but a straight line, and there is no critical point on the straight line except for points at the end of this line segment. So we'll have 2 points, minus 3, 9 and plus 3, 9 from this case. Now we'll find value of this function at minus 3, 9. It will be minus 18, and value of this function at 3, 9 will be plus 18. So now we have 2 more values. And if we'll take y as x square, we can write this function f as x, and we'll put y as x square. So it will be x square minus 3x. So this function f will be x cube minus 3x. F dash will be 3x square minus 3, and it is equal to 0. So we'll get the value of x as plus or minus 1. So one of the point, it will be 1, 1, and the other point will be minus 1, 1. So value of f 1, 1, it will be minus 2, and value of f minus 1, 1, it will be plus 2. So we have 5 values of this function, 4 values at the boundary curves and 1 value at the critical point. Now the least value in this case is minus 18. So absolute minimum value of this function will be minus 18 when the point is minus 3, 9, and its absolute maximum value will be plus 18 when the point is 3, 9. So this is how we find absolute maxima and minima for multivariable functions. Today we'll study relationship between coefficient of correlation and regression coefficients for simple linear regression using least square method, and we'll prove this result. Now suppose we have a data set of n observations and we have two variables, response variable y and predictor variable x. Now if we find mean of y, then mean of y is given by summation yi by n, and mean of x will be given by summation xi by n. Now if we plot these points and we draw lines on x bar and y bar, these two lines, they'll divide this entire plane in 4 quadrants, say 1, 2, 3 and 4. Now if we consider deviations of each variable, then we have xi minus x bar and yi minus y bar. And if we look at the quadrant, in the first quadrant, if we take any point, now this point, it is above y bar. So this yi minus y bar will be positive. And if we consider its deviation from x, xi minus x bar will also be positive. And their product, which is xi minus x bar into yi minus y bar will also be positive. So in the first quadrant, this product will be positive. Now in the second quadrant, if we take any point, then this y minus y bar will be positive. But if we consider x minus x bar in this case will be negative. So this value will be minus. So in second quadrant, this product will be negative. Now if we consider this third quadrant, in this third quadrant, this is below y and it is on the left of x bar. So both of them, they'll be negative. So this is negative and this is negative, and therefore their product is positive. So in the third quadrant also, this product xi minus x bar into yi minus y bar will be positive. And if we consider this fourth quadrant, in this quadrant, this xi minus x bar will be positive, but yi minus y bar will be negative. So this is positive and this is negative. So this value will be negative. So if we consider this product xi minus x bar into yi minus y bar will be positive in first and third quadrant and will be negative in second and fourth quadrant. Now this product xi minus x bar into yi minus y bar, which is product of deviations of x and y, this product, it captures linear relationship between x and y. Now if this linear relationship is positive, then most of the points they'll be in first and third quadrant. And if this linear relationship is negative, then most of the point they'll be in second and fourth quadrant. Covariance of x and y, it is defined as this summation I varies from 1 to n xi minus x bar into yi minus y bar upon n for population, and for sample will be n minus 1. So if covariance is positive, then there is a positive linear relationship between x and y. And if this covariance is negative, then there is negative linear relationship between x and y. Now problem with covariance is it only gives us direction of their linear relationship, whether it is positive or negative. It doesn't tell us the strength of this relationship, whether this linear relationship is strong or it is weak. And for that, what we do is we calculate covariance for standardized variable and we call it correlation coefficient. So what we'll do is, rather than taking variables as x and y, we'll define these variables zx as xi minus x bar upon sigma x and zy as yi minus y bar upon sigma y. Now if we define covariance for these standardized variables, we call it correlation and we write it as correlation of x and y, and this correlation will be given by this summation I varies from 1 to n, and then here will be xi minus x bar upon sigma x into yi minus y bar upon sigma y whole divided by n, which is this summation I varies from 1 to n xi minus x bar into yi minus y bar whole divided by n into sigma x sigma y. Now this is nothing but this is covariance of xy. So we can write this as covariance of xy upon sigma x sigma y, and we write this correlation coefficient as rho. So this rho will be covariance of xy upon sigma x, sigma y. Now we have this row which is coefficient of correlation. Now this coefficient of correlation, it not only tells us direction of linear relationship, it also tells us strength of linear relationship. Now this value of rho, it lies between -1 and +1. Now if rho is 1, that means direction is positive and they are strongly positively correlated. And if rho is -1, then there is a strong negative linear correlation between the coefficients. Now if coefficient of correlation is 0, what does that imply? Does that imply there is no relationship between x and y? No. Coefficient of correlation, it doesn't test relationship between x and y. Coefficient of correlation, it simply tests linear relationship between x and y. So if we say rho is 0, it simply means that there is no linear relationship between x and y. These x and y, they may be related, but they do not have a linear relationship. Say for example, if we take this data set of response variable and predictor variable, then in that case, if we find coefficient of correlation of x and y, this coefficient of correlation is 0. But if we draw the graph of x and y, then we see this graph will be a parabolic graph opening downwards, which is y equals 50 minus x square. So in this case, these two variables, x and y, they are definitely related. Y equals 50 minus x square, but they are not linearly related. So when coefficient of correlation is 0, it simply means that they are not linearly related. They may have other functional relationship. Now here we'll prove relationship between coefficient of correlation and regression coefficient in simple linear regression. So what we'll do is we'll consider a simple population response function which is given by yi, and it is equal to beta naught plus beta 1 xi plus ei, which is this error. Now we'll estimate these two parameters beta naught and beta 1 using method of least square in case of classical model of simple linear regression. Now in least square method, what we do is we estimate these parameters beta naught and beta 1 by minimizing squares of this error ei. So suppose we have some function s, which is a function of beta naught and beta 1, and it is this summation ei square, and it will be given by this summation yi minus beta naught minus beta 1 xi whole square. Now in method of least squares, we wish to minimize this sum of squares of vertical distances or sum of squares of these errors. So we need to minimize this function. So for that, what we'll do is we'll differentiate this function partially with respect to beta naught. So we'll write delta s upon delta beta naught will be this summation, and here will be 2 times yi minus beta naught minus beta 1 xi, and then derivative of this function with respect to beta naught will be simply -1, and we'll put it equals to 0. Now suppose the minimum value of this function, it occurs at beta naught cap and beta 1 cap. So from here we can write this summation yi minus beta naught cap minus beta 1 cap xi, it must be equal to 0. Now we can write this as this summation yi minus summation beta naught minus, we can take beta 1 cap common, and then it will be this summation xi will be equal to 0. Now summation yi, it is nothing but it is n into y bar minus, now beta naught, since it is constant, we can write this as n into beta naught minus this is beta 1, and summation x is simply n into x bar, and it will be equal to 0. So we can take this n common. So from here we can say this beta naught cap will be y bar minus beta 1 cap into x bar, and this is our first equation. Now we'll differentiate this function with respect to beta 1. So we can write del s upon del beta 1 will be this summation, and then again first we'll differentiate this power, will be 2 times yi minus beta naught minus beta 1 xi into derivative of minus beta 1 xi will be minus xi, and will be equal to 0, and our parameters are beta naught cap and beta 1 cap. So we can actually write this as this summation yi minus beta naught cap minus beta 1 cap xi into xi, and it will be equal to 0. Now what we'll also do is we'll put the value of beta naught as y bar minus beta 1 cap x bar. So we'll actually write this as this summation yi minus, now beta naught bar is y bar minus beta 1 cap x bar. So it'll be minus y bar, and then minus minus plus will be beta 1 cap x bar minus beta 1 cap xi into xi will be equal to 0. Now we can write this as this summation xi yi minus y bar xi plus beta 1 cap x bar xi minus beta 1 cap xi square, and will be equal to 0. Now we can write this as this summation xi yi minus this y bar summation xi plus beta 1 cap x bar into summation xi minus beta 1 cap summation xi square, and it will be equal to 0. Now this is summation xi yi minus this is y bar, and summation xi is n into x bar plus, now this is beta 1 cap x bar, and this is n x bar minus, and here will be beta 1 cap summation xi square, and it will be equal to 0. Now from this we can write beta 1 cap. So this beta 1 cap will be this summation xi yi minus n x bar y bar upon summation xi square minus n into x bar square. Now if we recall, covariance of xy, covariance is given by this summation xi minus x bar into yi minus y bar whole divided by n. Now this is this summation xi yi minus x bar into summation yi minus y bar into summation xi, and then plus summation x bar y bar whole divided by n. So it will be this summation xi yi minus, now summation yi is n y bar, so it will be minus n x bar y bar, and summation xi is n x bar, so it will be minus n x bar y bar, and plus summation x bar y bar is n times x bar y bar, so it will cancel whole divided by n. So this numerator we can write this as n into covariance of xy. So this beta 1 cap will be n into covariance of xy. Now in the denominator we can write this as this summation xi square. If we take n common, we can write this as xi square by n minus x bar square. Now this n and n will cancel. Now this is nothing but this is variance of x. So this beta 1 cap, it is nothing but it is covariance of xy upon sigma x square. So this beta 1 cap, it is covariance of xy upon sigma x square. Now what we'll do is we'll multiply and divide it with sigma y. So we can write this as covariance of xy upon sigma x, sigma y into sigma y upon sigma x, and this is nothing but this is coefficient of correlation. So we can write beta 1 cap will be rho into sigma y upon sigma x. So now we have estimated beta 1, and from beta 1 we can calculate beta naught cap, and which is y cap minus beta 1 cap x bar. So this is how we estimate parameters using least square method, and this is the relationship between coefficient of correlation and regression coefficient in classical simple linear regression model. We have studied how to find maxima and minima for a function in one variable as well as in more than one variable in calculus. Now, there are many practical situations where we need to find maxima and minima of a function subjected to a given constraint. Say for example, suppose we are given a function, say fxy, and we need to maximize or minimize this function, and we call this function as objective function, subject to the constraint gxy equals 0. So this is our constraint. So in these questions, we need to find maxima and minima of this function f when gxy equals 0. Now we solve such questions using Lagrange's method, and in this we define a Lagrange's function L xy lambda as this function f, which in this case is a function in two variables f xy, and then plus or minus lambda, and then this given constraint, which in this case is gxy. So this is a Lagrange's function, and this variable lambda, it is called as Lagrange's multiplier. Now what we'll do is we'll find gradient of this function and we'll put it equals to 0. So we'll define del L by del x and we'll put it equals to 0. Del L by del y equals 0 and del L by del lambda equals to 0, and we'll solve these conditions to find maxima and minima of this function subject to this given constraint. So basically, once we have defined this function in terms of x, y and lambda, we can use multivariable calculus to find maxima and minima for this Lagrangian function. So all the concepts we have studied in multivariable calculus like Hessian Matrix and all, they'll come handy in this situation. I'll provide the link to the multivariable calculus playlist in the description below. Now there are numerous applications of Lagrange's method. So what we'll do is we'll take up an example from microeconomics and then we'll try and apply Lagrange's method for optimization problem. Say for example, we are given that a firm uses two inputs K and L of capital and labor respectively to produce a single output Q according to the specific type of production function Q, K to the power A and L to the power B, where A and B they are greater than 0. Now we are also given that prices of capital and labor, they are R and W respectively. Now it says we need to find cost minimizing inputs of capital K and labor L. So first we need to define what is our objective function in this. Now our objective is to minimize cost, and cost, it is given by cost of capital, which is R into K, plus cost of labor into quantity of labor, which is L. So this is our objective function subject to the constraint that Q is K to the power A and L to the power B. So now it becomes a candidate for Lagrange's method. So in this case, we'll first define Lagrangian function. So it will be this L. Now it is a function of K, L and lambda, and we'll write this as this RK plus WL, which we need to minimize, and then plus lambda, and then this equality constraint, which is Q minus K to the power A into L to the power B. Now we'll find its gradient. So we'll find del L by del K, and it'll be this R minus lambda, and it'll be A K to the power A minus 1 into L to the power B, and it'll be equal to 0. So from here we can write R equals lambda a k to the power a minus 1 L to the power b, and that's our first equation. Now we'll differentiate this function with respect to L. So we'll write del Lagrangian function upon delta labor, and L be equal to W minus lambda, and L be equal to B into k to the power a L to the power b minus 1 equals 0. So from here we can write this W will be equal to lambda b k to the power a and L to the power b minus 1, and that's our second equation. And then we'll differentiate this function with respect to lambda. So we'll write del L upon del lambda. In this case we'll get q minus k to the power a L to the power b equals to 0, which is nothing but our constraint equation. So which is q equals k to the power a and L to the power b, and that's our third equation. Now what we'll do is we'll divide first with second. Now if we divide first with second, we can write r upon w lambda a k to the power a minus 1 L to the power b upon lambda b k to the power a L to the power b minus 1. Now this lambda will cancel. Now k to the power a minus 1 will cancel, and L to the power b minus 1 will cancel. So from here we can write k upon L will be equal to AW upon BR, and that's our fourth equation. Now from this we need to find K and L, and we know that K to the power A into L to the power B is Q. So what we'll do is we'll take this function to the power B both sides. We can write K to the power B upon L to the power B will be equal to AW upon BR whole to the power B, and then we'll multiply and divide K to the power A in the left hand side. Now k to the power a into L to the power b, it is nothing but q. So from here we can write k to the power a plus b will be equal to q into AW upon BR whole to the power b. So from here we can write cost minimizing input capital K as q to the power 1 upon a plus b into AW upon BR to the power b upon a plus b, and this is our first answer. Now we'll also need to find cost minimizing input of labor. Now we know that k upon L is AW upon BR, so we can write L as k into AW upon BR to the power minus 1. So it will be q to the power 1 upon a plus b into AW upon BR b upon a plus b, and then this minus 1, so it will be this minus a. So we can write L as q to the power 1 upon a plus b upon BR by AW to the power a upon a plus b, and that's our cost minimizing of labor L. And this is the second question. Now third question is we need to write down cost function of the firm. Now we know that cost function is RK plus WL. So we can write cost function of this firm as R into K, and K is q to the power 1 upon a plus b into AW by BR to the power b upon a plus b, and then plus WL, and L is q to the power 1 upon a plus b into BR by AW to the power a upon a plus b. Now we'll take q to the power 1 upon a plus b common, so we can write this C as q to the power 1 upon a plus b. Now this is r to the power 1 upon r to the power b upon a plus b. So it will be r to the power a upon a plus b, and it will be w to the power b upon a plus b, and here it will be a upon b to the power b upon a plus b. And the same way it will be w upon w to the power a upon a plus b. So it will be w to the power b upon a plus b r to the power a upon a plus b into b upon a to the power a upon a plus b. Now here we can take this common. So we can write this cost minimizing function c as q to the power 1 upon a plus b into r to the power a upon a plus b w to the power b upon a plus b into a upon b to the power b upon a plus b plus b upon a to the power a upon a plus b, and that is the answer to this question. So we have worked out all the three cases. So once we are given an objective function with an equality constraint, we can always use Lagrange's method to find its optimal solution. Hello and welcome to the world of mathematics. I present my website www.mathsmarizing.com and my YouTube channel Mathsmarizing for your kind perusal. If you like them and are inspired by the possibilities, then consider subscribing and sharing it with someone you know who might benefit from it. Thank you. Now another problem where we can apply Lagrange's method is in utility maximization or expenditure minimization problems. Now in this case we are given a utility function which is given as ux and it will be equal to under root x1 x2, where x1 and x2 are quantities of two goods. Now w is a fixed wealth and prices are p1 and p2. Now the first question is solve utility maximization problem. Now in this case we have to maximize this utility. So here our objective function is ux and it will be given by under root of x1 x2. Now subject to the constraint, what is the constraint in this? Now this maximization of utility, it is subject to budget constraint, and budget constraint is this wealth is fixed. So this w will be equal to p1 x1 plus p2 x2. So now we have our objective function and we also have our equality constraint. So for this problem we can write Lagrangian function as L x1 x2 lambda, and it will be equal to this optimization function under root x1 x2 and then plus lambda and this equality constraint which is w minus p1 x1 minus p2 x2. Now we'll find its gradient and we'll put it equals to 0. So first we'll find del L by del x1 will be under root x2 upon 2 under root x1 and minus lambda p1 equals 0. So from here we'll write lambda p1 as under root x2 upon 2 under root x1, and this is our first equation. Now we'll differentiate it with respect to x2. So it will be under root x1 upon twice under root x2 minus lambda, and here it will be p2 equals 0. So it will be lambda p2, and we can write this as under root x1 upon twice under root x2, and that's our second equation. Now we differentiate it with respect to lambda, then we'll get this as w minus p1 x1 minus p2 x2 equals 0, which will give us our original constraint equation, which is our budget constraint in this case. So this is our third equation. Now what we'll do is we'll divide first with second. So from here we can write p1 upon p2 will be equal to x2 upon x1, or simply we can write p1 x1 will be equal to p2 x2. Now we put it in this third equation. So from here we can write p1 x1 will be equal to p2 x2, and it will be simply equal to w by 2. So from here we can write utility maximization quantities x1 will be w upon 2p1 and x2 will be w upon 2p2. Now we can also find Lagrange's multiplier. We can write lambda as 1 upon 2p1 under root of x2 upon x1. Now under root x2 upon x1 will be under root of p1 upon p2. So it will be 1 upon 2p1 into under root of p1 upon p2. So the value of Lagrangian multiplier will be 1 upon 2 under root p1 p2. So for this utility function, if we consider utility maximization problem, then utility will be maximized if we consider these quantities x1 and x2. Now with the same setup, it can also ask us to find expenditure minimization problem. Now in this case, we have to minimize expenditure. Now expenditure will be given by p1 x1 plus p2 x2, subject to this constraint u equals under root of x1 x2. So for the second part, basically objective function and constraint, they are interchanged. So now here we need to minimize this expenditure. So again we'll write Lagrangian function. So Lagrangian for this will be p1 x1 plus p2 x2 and then plus lambda will be u minus under root of x1 x2. Now again we'll differentiate this with respect to x1. We'll get this as p1 minus lambda under root x2 upon 2 under root x1 and will be equal to 0. So from here we get p1 equals lambda under root x2 upon 2 under root x1, and that's our first equation. Now if we differentiate this with respect to x2, we'll get this as p2 minus lambda under root x1 upon twice under root x2 will be equal to 0, or we can write p2 equals lambda under root x1 upon 2 under root x2, and that's our second equation. Now we differentiate this function with respect to lambda, we can write this as u minus under root x1 x2 equals 0, which will give us our third equation, which is u equals under root of x1 x2. Now from these three equations we have to find x1 x2 and we have to find the value of lambda. Now if we divide this first equation with second, we can write p1 upon p2 will be equal to x2 upon x1. Now here we can write x2 as p1 x1 upon p2. So x2 will be p1 x1 upon p2, and if we put x2 in this equation, we can write u equals under root of p1 p2 and it will be equal to x1. So from here we'll get expenditure minimization quantity x1 as u into under root p2 upon p1. So that's your x1. And in the same way we can write x2 as u into under root of p1 upon p2. So now we have our quantities x1 and x2. Now we have to find the value of lambda. So basically we can write this lambda as 2p1 and into under root of x1 upon x2. Now under root of x1 upon x2 will be under root p2 upon p1. So it will be twice p1 and will be under root p2 upon p1. So value of lambda will be 2 times under root p1 p2. So that is the value of Lagrangian multiplier. Now let us consider another question, in which is a consumer has preferences given by the constant elasticity of substitution utility function u is a function of q1 q2 and will be under root q1 plus under root q2 whole square, which we can also write as q1 plus q2 plus 2 times under root of q1 q2. Now it says write the Lagrangian for consumer's maximization problem. Now it doesn't say what maximization, so we'll assume it is consumer's utility maximization. And here we are not given prices and wealth, so let us say budget constraint is W and the prices are P1 and P2. So basically our objective is to maximize U, which is Q1 plus Q2 plus 2 times under root of Q1 Q2, and our budget constraint is W equals P1 Q1 plus P2 Q2. Now we'll write Lagrangian function, so it will be Q1 plus Q2 plus 2 times under root of Q1 Q2 and plus lambda, and here will be W minus P1 Q1 minus P2 Q2. Now we'll find its gradient and put it equals to 0. So first we'll find del L upon del Q1, and it will be 1 plus, and it will be under root Q2 upon under root Q1 and minus lambda P1, and it will be equal to 0. So from here we can write lambda P1 will be equal to under root Q1 plus under root Q2 upon under root Q1. Now from symmetry, if we find del L, del Q2 and put it equals to 0, we'll get lambda P2 as under root of Q2 plus under root Q1 upon under root Q2. Now if we divide first with second, we can write P1 upon P2 will be equal to under root of Q2 upon Q1, and this is our first equation. Now we differentiate this with respect to lambda, we'll get del L by del lambda, and it will be equal to W minus P1 Q1 minus P2 Q2 equals 0, or P1 Q1 plus P2 Q2 will be equal to W, and that's our second equation. Now using these two, we have to find the value of Q1 and Q2. Now if we square this, basically we can write Q2 as P1 upon P2 whole square into Q1. So we can write this equation as P1 Q1 plus, now P2 Q2 will be P1 square Q1 upon P2, and it will be equal to W. Now we can write this as P1 upon P2 into P1 plus P2 Q, and it will be equal to W, or the value of Q1 will be P2W upon P1 plus P2. So that's our value for Q1. Now Q2 is simply P1 square upon P2 square Q1. So we can write this Q2 as P1W upon P2 P1 plus P2. So now we have the values of Q1 and Q2. Now once we have the value of Q1 and Q2, we can use the value of Q1 and Q2 to find the value of lambda. For this question, we just need to find optimal quantities in terms of prices and income.